Hello, welcome to our webinar. My name is Sherry Kraber, and I am a statistical consultant with StatEase Incorporated, and I want to thank you for coming today. Today's topic is using DOE, specifically response surface designs, to predict process performance. We're going to learn about using response surface designs for making predictions, and that includes the big topic of how to size designs correctly for making these predictions. We're going to experience a response surface case study that has been sized correctly, and we will walk through the analysis, the optimization, and conclude with making predictions from this and showing that they are indeed as precise as we are interested in. So during this session, we have the audience muted. You can put questions into the question box, and I will answer them probably at the end of the session. And if you have any further questions, you can send them to me. My email will be at the end of the presentation. So let's give a brief introduction to design of experiments in general. The strategy of experimentation generally looks something like this, where you start with screening or characterization designs. These are generally factorial designs, fractional factorial designs, and they are used to detect effects. The focus of today's session is actually going to be down here in the optimization area, where we are looking at response surface methods. When we size designs for screening and characterization, we use a statistic called power. When we size designs for optimization, we're going to use a different statistic called precision via the Fds graph. So let's compare the differences in DOE objectives. When we're using factorial designs, the primary interest is looking at either screening designs or characterization designs to identify our main effects and our interactions, specifically the two-factor interactions. The response surface designs, on the other hand, are used for optimization, and the emphasis shifts to fitting a good response surface and making predictions. So we change our emphasis from asking what are the important process factors to how well does this surface represent the true behavior of the system. So for factorial designs, we have a statistic called power, and that's the ideal metric to evaluate design suitability. But with response surface designs, power doesn't answer the right question. Power is the ability of a design to detect an effect. We want to answer how well can this design make good precisions. And to answer this question, precision is a better measure of the goodness of the experiment design. So moving into response surfaces, if our goal is to make precise predictions, we are using a response surface to model or fit a polynomial relationship between the factors and the responses. So if we have just one factor, we would get a shape something like this. When we go to multiple factors, we can model that in 3 dimensions with something like this. And we are interested in making predictions all along the factor range, whether that's in one dimension or in multiple dimensions. Now, we're usually trying to optimize our system, but you don't know the true optimum in advance. If you knew the true optimum, you wouldn't have to be doing the designed experiment. So we are collecting data and fitting the polynomial in order to discover the true optimum. So the location is unknown. Because the location is unknown, we want to evaluate how much of the design space can predict our response with some specified precision that we have to define. And the precision of our prediction depends on both the location in the design space of the optimum and the standard deviation of the response. So if we keep this simple and just picture a linear effect, we would fit a straight line, fit the linear effect, and the dotted lines here are the confidence band, the confidence interval for our predictions. Note that these confidence intervals change depending on where we are along the level of factor A. So if we are predicting in the middle of factor A, then the confidence bands, the dotted lines, are closer together. And as we go out to the edges of factor A, the dotted lines get farther apart. In this case, only about 50% of the fraction of design space falls within our desired range, which is this plus or minus D. So D is the amount of precision that we want to estimate. We'll illustrate that over the next couple of slides. But you can see D is generally considered constant over the design space, when whereas the confidence interval is not constant. So the place where they overlap, so right about here, from roughly 0.25 to roughly 0.75, that middle area of the design space is being estimated precisely enough, whereas the edges are not. A guideline to size a response surface design, we usually want to have enough runs so that we can achieve this area where we're getting good predictions to cover about 80% of the design space. We can calculate this area by knowing two things, our D and our S, or our precision, our desired precision, and our actual response standard deviation. So let's look at those two numbers. So our precision D, the question is, how well do you want to make precisions? Or how well do you want to make predictions? The more precision you want, the more data is going to be required. So you might say something like this: we want to estimate the mean response with a precision, which is our D, of plus or minus 0.8. Now, whatever this plus or minus is, that's purely a business decision. It is not a statistics decision. It is based on subject matter knowledge and the amount of precision that you're interested in. The standard deviation is something that you can calculate, on the other hand. This is the process or the response standard deviation. It includes both sampling and test variation. It's typically estimated with historical data or from prior DOEs or other means. The larger the standard deviation, the more data is going to be required to get good estimates. So we might say that historical data shows a standard deviation of 0.5. So now we have our two numbers, our D and our S. And in just a little bit, I'll show you how we're going to put those into our Fds graph. Here are a couple more examples for D and S. So you might have a viscosity measurement, or a percent conversion, or maybe a percent yield. Might have flex modulus, average thickness, you know, whatever your response measurement is, you have to determine what is your desired plus or minus precision. Then you also have to take some historical data or look at a previous designed experiment and calculate the standard deviation. Okay, so somehow you need to get those two numbers. Prior to having this statistic of FDS, we used to look at standard error graphs. So this is the standard error of a simple two-factor face-centered central composite design. And this graph shows you the area of the design space that has a standard error of 0.45. You can follow this contour line. And then the next contour line is a standard error of 0.5, and the next 1.6, the next 1.7. And we can look at this in 3 dimensions over here, and you can see that this is like a topographical map. Wherever we have lower standard error, that's where we're going to have more precise predictions. But you know, this graph, the standard error graph, works great when you only have 2 factors. But many of us have 3, 4, 5 factors, and then the use of the standard error plot would involve looking at it in all these different directions. You'd have to look at it in the AB direction, AC, AD, BC, BD, etc. All these different directions, which people just don't do from a practical standpoint. So statisticians figured out how to take the information on this graph over multiple dimensions and accumulate this area and calculate how much of the multi-dimensional area can be achieved. So we can plot this on an FDS graph. FDS is the fraction of design space, and on the X or on the Y-axis here we have our standard error. And so here we have the standard error of 0.43, and I can see that that contains about 25% of the design space. The next line of 0.5 contains about 50% of the design space, and so on. So we can put in our desired precision and our standard deviation of our response, and those two numbers get calculated into changed into a standard error of a mean, and then we can calculate how much of the design space is going to be fit. So with our desired plus or minus prediction of 0.8 and our standard deviation of 0.5, if we put that into Design Expert for a particular design, it will give us a graph that looks like this, and it will show us the value right here at this point, which is, you can't read it very well here, but it's 0.89. So that says 89% of the design space predicts with a precision of 0.8 or better. And our goal when we are sizing response surface designs is that we want at least 80% of the design space to provide the good predictions, whatever value that we're looking for. In this case, 0.8 relative to the standard deviation of 0.5. So if FDS is greater than 80%, then the design is working well. So as I just said, how good is good enough? Here's a couple of rules of thumb. If we are just looking for an optimum, and so we are exploring our region, our area of interest, then a general rule of thumb is to get an FDS greater than or equal to 80%. So that you have at least 80% of the design space giving you the predictions that you want. If your goal is to verify or validate an entire region, then you would want the FDS to be closer to 95 to 100%. So the desired FDS does depend on what the objective is of your experiment. If you need to improve precision, then there's basically three things you can do. You can increase your D, so accept that you can estimate things with a little bit larger plus or minus precision, not quite as small as you hoped for. You can try to reduce the noise in your system. Or what most people do is you can increase the number of runs in the design. So maybe add 4 or 5 runs, especially if you're running like an optimal design. It's easy to add additional model points to those designs or augment with a few more runs. All right, so let's go through a response surface design. We will start by sizing the design. Then I will walk through the analysis and optimization, which are just necessary in order to get to the final optimum. And then we can use that to make predictions and confirm that, yes, those predictions were made as precisely as we were looking for. I have attached to this presentation, I do not plan to go over it, but I've attached to it an appendix comparing some common response surface designs. So if any of you have questions about what type of response surface design is appropriate, there are some follow-up slides that you can look at after I've loaded the slides onto our website. All right, this case study is actually one of our tutorials. So if you want to duplicate this, you can simply go into the software. Actually, I will pull Design Expert right now. To find the tutorials, you go into the help, you go to tutorials, and we're going to look at this response surface chemical conversion tutorial. And the data for this is found under tutorial data, chemical conversion. So here's the design with the data, and then here's a fully analyzed file for you. All right, so I just want to make sure that you can duplicate this if you would like. It has 2 responses, the percent conversion and the activity. There are 3 factors that we're looking at: the time, temperature, and catalyst. And this is run as a central composite design in 2 blocks, where we have 12 runs done in the first block and then another 6 runs done in the second block. So we have two responses. The first response, we want to maximize the percent conversion, and we want our percent conversion ultimately to be greater than 80%. And then we are trying to get a target activity level of 63 with an acceptable range between 60 and 66. Okay, the precision of our predictions. We want to predict average conversion plus or minus 5%, and we want to predict average activity plus or minus 1.3. The standard deviation of each of these is 4 and 1.1 respectively. The factor ranges are listed here: 40 to 50 minutes, 80 to 90 degrees, 2 to 3% catalyst. We're going to use this central composite design to create up to a quadratic polynomial. So let's look at this from a sizing perspective. This is where we need to take into account these pieces of information. And specifically, we figure out the signal to noise ratio. So if we take 5 divided by 4, that signal to noise ratio is 1.25. We take 1.3 divided by 1.1, that signal to noise ratio is 1.18. This is the worst case. This is the smaller signal to noise ratio. So that's the one we want to check. You know, any responses larger with a larger signal to noise ratio will be fine if we can show that this smallest one is fine. So we would go into, so here's my design, and you would do these checks prior. In fact, I'm going to actually delete this data. Because we would do this check prior to getting any data. It's you size a design before you do the work. So we built this design, and then to size it, you go to evaluation, and then you go to graphs, and you have the FDS plot. You find your FDS tool, and we're going to type in that D of 1.3 and the S of 1.1. And it puts the crosshairs on appropriately and shows us that the FDS, the fraction of design space, is 0.85. That tells me 85% of the design space will be able to predict this response, this activity response, to within plus or minus 1.3. Assuming that the DOE standard deviation is about 1.1. You know, and that's information that's coming in prior to running the experiment. Okay, I mean, if we wanted to check the power for conversion, we just put in the other numbers. So we could put in 5 and put in 4, and that precision, or excuse me, that fraction of design space is 91%. So 91% of the design region will be able to predict conversion to our desired precision. Okay, so again, that's found under design evaluation. You simply click there and you can immediately click on the graphs. All right, now that we know this design is sufficient, we can then go out and do the work and collect the data. So let me just reopen this with data in it. There we go. And we will start the analysis. So we're going to come down here to conversion. This is version 13, so we're going to click on the Start Analysis button, which brings us to our fit summary. And the quadratic model is a suggested model. It's got a significant lack of, or significant p-value. It has no significant lack of fit, and it has good adjusted and predicted R-squareds. So that's a good starting point. We're gonna go ahead and use that. Whatever the software suggests is the default model. And we can see that we have many significant terms. I will just say that in general, I do advise model reduction. So, there are a couple of terms that could be removed. When there are only a couple of terms, that doesn't really matter. But if there are a lot of insignificant terms, then I would highly recommend that you go back and reduce the model using some of the auto select methods. We'll leave it here as is for right now. The adjusted R-squareds, as I pointed out, are nice and high. They are in reasonable agreement with each other. And the diagnostic plots, this is a pretty straight line, reasonably straight. Sometimes we have little tails. That's not to be of concern unless the Box-Cox plot indicated the need for a transformation. Residuals versus predicted looks good, and residuals versus run has no trends. And as I mentioned, the Box-Cox plot says the recommended transformation is none. So with all of those plots looking decent, I would go ahead and just build my model graphs. Now, we are going to end up using optimization. So I'm not going to spend a lot of time looking at that model graph. Instead, I'm going to go ahead and analyze activity. For activity, it looks like the linear model is suggested. You can see that if we go to a 2FI or a quadratic model, that you get into non-significant p-values. So we don't need to go to a higher order model. Linear should be sufficient. And again, A and C are the important terms. B is not important. And lack of fit is not significant, which is good. Adjusted and predicted R-squareds are even higher, 0.9s. That is awesome. The diagnostics show a nice straight line. No, or it has constant variance, no expanding variation, and no trends on the run chart. So all the diagnostics are good. And again, we have no recommended transformation. So it gives us another model graph. This is the one factor plot. We don't, we can put this into a contour plot, but I would want to use the contour plot of A and C as those were the two things that were significant. So I am going to right click on C and put that on the X2 axis. So we can get our AC graph, and in 3 dimensions it looks like that, just a flat plane. All right, with the analysis complete, we can then move on to optimization and put in some goals. So the goal for conversion is certainly going to be to maximize it. And we would like conversion to be greater than 80%. And I mean, if we can get up to 100, I would certainly like that. Notice that the software by default puts the limits of 51 to 97. I would rarely use those default limits. It's always better to change the limits to reflect what you actually want. Usually, well, like with a maximize, I don't want any solutions that have a percent conversion way down here at 51%. The lowest acceptable percent conversion is 80%. So certainly make sure to change that lower limit to an 80 to cut off all of these potential solutions down here, which are not acceptable to me. So make sure that the limits you enter are reflective of what you want out of the process. Then for activity, we wanted to target a 63. But again, don't use the default limits. You want to set the limits to be exactly what you want, which is 60 to 66. That was the range that was acceptable. And then we can look at the ramps view of our solutions. And we can see that if we set time to about 47 minutes, temperature to 90, and catalyst to about 2.7, so it's 2.68, somewhere in there, then we should get a conversion of 91 and activity right at 63. Okay, let me go back to my slides. So we have checked all of these diagnostics. We've built the graphs and optimization. People ask, you know, what's the basic criteria to be able to use optimization? And so we say you should have a significant model, which means a p-value less than 0.05. You should have insignificant lack of fit, p-values greater than 0.1. R-squareds greater than 0.5 is just a guideline. And then well-behaved residuals, meaning the diagnostic plots don't have outliers or any strange things. So we confirmed all of those criteria. On the report view, solutions are reported or sorted by desirability. Desirability goes from most to least, and the higher the desirability means the closer all the goals have been met. So you can see that we get activity of 63, pretty much across everything. Conversion is 91 at the top, but goes down to 87 as you get to some lower desirability numbers. People do think that they need to maximize desirability, and that is absolutely not true. Desirability is just a relative ranking of the solutions that were found. So it doesn't matter if your desirability is 0.7 or 0.3. The solutions at the top are more desirable than the solutions at the bottom. And so that is what you should focus on, not the actual value of desirability, which is just a mathematical evaluation of how close these final numbers were to the goals that you set. Okay, so now that we found an optimum, we have to put that optimum into point prediction. So we can use our our top solution. That's going to be in here by default. So let me pull that up. So we are going to go to point prediction. And the solution number one over on your factors tool, solution number one is set up by default. And so we can see that that's at time of 42, temperature, and catalyst. Now, if you wanted to change that just a little bit, you certainly can. You just click on the sheet mode, and we could put in a value more precisely at 47, and maybe 2.7 would be desirable. Depends on how precisely you can control that catalyst. Then you click on OK, and down below you'll see that you get a 95% interval. This 95% interval says that we are predicting our mean at 91 for conversion and 63.05 for activity within this interval. And I moved it slightly off of the default. So we'll go back to that. At that default, we'll look at the 95% interval for that. We had, at the beginning of the problem, stated that we wanted to predict average conversion plus or minus 5%. So if we look at this predicted mean and we look at this 95% confidence interval, that interval is plus or minus 4.5%. So we succeeded there. And then for activity, we wanted to predict plus or minus 1.3. And we actually, at this spot, predict activity at plus or minus 0.8. So again, we achieved the results for activity. All right, so summarizing in general response surface methods, the key thing between factorials designs and response surface designs is that we change our objective from simply detecting effects, which are either main effects or interactions, to now really describing the relationship between the factors and the responses and making predictions. Even finding an optimum, but finding an optimum is all about making predictions. Response surface designs are larger than factorial designs, so we usually have narrowed ourselves down to just a handful of critical factors. And we are modeling this polynomial model, whether that's anywhere from a linear to a two-factor interaction to a quadratic model, or potentially even a cubic model if you use the right design. And this is really going to allow us to maximize, minimize, achieve whatever results, whatever goals we are wanting out of our responses. So response surface designs are the perfect tool for making predictions as long as they have enough runs. You need to provide two pieces of information in order to size. You need to define the precision that you want. So you think about your average response plus or minus some D, some precision. And then you also need to estimate the standard deviation of the response from some historical data. If you enter this information, the Fds graph will tell the percent of the design space that will give predictions with that precision or better. And the goal is generally 80% of the design space or better. My final comment here is that the value of this FDS tool increases as your signal to noise ratio decreases. very specifically, as your signal to noise ratio is less than about 1.5, that is where the default response surface designs might need to be augmented with some additional runs. You need to check it. You need to verify that your central composite or your box Banken design or your optimal design, check to make sure that they have enough runs. If your signal to noise ratio is 1.5 or greater, then the designs usually have enough runs that they're going to be sufficiently large. All right, so that concludes my official presentation about using the fraction of design space to size your response surface designs. If you have any questions, you can type them into the question box and I will answer them. Otherwise, I thank you very much for the time that you've spent with me today. Okay. If you have any questions later on, you are welcome to email me using sherry@statease.com and I will reply to you directly. Thank you very much.